Questions on this? Yeah, everybody will be able to assess with their data. What if you have a nominal variable? Should you make this assessment?
No.
Don't do it. Only do those variables that you consider continuous, right? Interval ratio.
And you said this is cool. This data, you think it looks okay? You really transform it? I mean, it's 80.
I think it looks all right. I mean, it's sort of truncated, but I know it's voters, and you have to be 18 and older to vote, so that's why the low end is sort of odd. If we had the low end filled in, it would be perfectly fine, I think. So I think it looks a lot better than a lot of histograms that I've seen, because you can see some pretty odd histograms. And so I would probably, if this was the only variable I had problems with, I'd probably be just fine leaving it exactly like it is. But it's a judgment call. Somebody else might make the call, hey, this is significant, let me try to take the square root transformation of it, or the inverse transformation of it, or the log, or some other transformation to see if I can make it more normal. And that would be a judgment call that is probably certainly justified. Wouldn't be sort of crazy to want to do that. All right. So then, just a quick primer on skewness or skewness and kurtosis. So skewness is symmetry, right? Positive skewness indicates longer tails off to the right. In general, what's happening is the mean is greater than the median, right? So you have a mean value that is, or the mean ends up being larger because of that tail. And so if you look at just the mean and the median, in most cases, not all cases, if it's not severely skewed, or if it's not significantly skewed, it may not always be this, but in general, the mean in this case is greater than the median. The median is the middle point in your data, and if you have a bunch of scores on the high side of your data that is pulling the mean in one direction, that mean is going to be greater than the median. And negative skewness indicates, again, longer tails off to the left. In general, what's going on, or in general, this can be identified by thinking about the mean and the median again. In this case, the mean is less than the median. Those scores on the low side of that tail that goes way out to low scores it's pulling your mean in that direction. But the median is staying right in the middle of the data, and therefore mean would be less than median. And so what we're going to talk about here in a little bit is transformations that we can do for the data. And in some cases, the median is a better estimate of central tendency than the mean. Right? If the mean is being influenced by a distribution with tails off to one direction or the other, then the median might be a better estimate of central tendency. And so if your judgment is that, then it makes perfect sense to transform the variable in some way to make the mean closer to the median. The median isn't going to change. That value might change, that's the median, but the person or the thing isn't going to change. They're always going to be the middle person or the thing in the data, and we're going to just try to make the mean closer to that. And that's the rationale for doing transformations. So kurtosis, again, is a measure of how peaked or flat the data is. Negative values indicate, again, flat distribution. Positive values indicates that the distribution is more peaked than normal. Make sense? Should be review. So this is this is where we try to fix problems with non-normal data. If you identify that your variable is non-normal, and if you come to the conclusion that the median is a better measure of the central point than the mean, then it makes sense to do a transformation to try to get the mean closer to the median value. And just about all of the statistics that we deal with use the mean score, right? So we calculate an average, and we use that average or the mean when we calculate standard deviation, right? Because the standard deviation is each score minus the mean. And when we calculate sums of squares, which we'll talk about, and which you read some about today if you read the Fedhazer chapters, when we calculate sums of squares, again, that's using the mean. And so all of the statistics that we use, many of the statistics that we use rely on the mean. And if the mean isn't a good measure of central tendency, and the median is a better measure of central tendency, then we ought to try to make the mean and the median to be equal. Then that mean value that's going to be used in all of our statistics will be a more accurate representation of the central point of the data, as opposed to some skewed value that is a lot different than the median value. So when a variable is not normally distributed, we can use a transform variable to replace it. But sometimes we can't fix problems with normality. So just because you try to transform the variable doesn't mean you're going to be able to fix it. Sometimes there is no fix. And so you still need to test the transform variable for normality. And if the transform variable is normally distributed, we can substitute it in our analysis. And we'll talk a little bit about when to do this and when not to do this, and potential issues that one might run up against when you try to do this. What's the first thing that comes to mind when I say we can transform variables and we can substitute those variables in for our analysis? What's the first thing that comes to mind? Elena?
Being unethical.
Really? How about cooking the books?
Cooking the books, same thing, right?
Yeah. And so it is. That is a very, very typical reaction. Cooking the books, and cooking the books is definitely unethical. So the two are. For some reason, cooking the books feels a little bit better than somebody saying. If I were to be accused of one or two things, either cooking the books or being unethical, I'd rather be accused of cooking the books, right? For whatever reason. But they're right. If you're cooking the books, you're unethical. Yeah, you're unethical. Yeah. This isn't cooking the books, though. So my hope is I'm going to do my best to convince you that this is not cooking the books, that it makes perfect sense, and in some ways, if you don't do it, you're sort of cooking the books, being unethical. That might be a stretch, but it certainly is, and it all comes down to when you look at your data, what's the best measure of the central point in your data? And if you say that it's the mean, then it doesn't make any. Don't do this transformation. If you say, hey, I think with my data, I think the better measure of the central point isn't this, because this is 46.5. It's being pulled this direction because we have more people out on this tail than we do on this tail. And so I might say the better measure of central tendency is this measure, 45, which is the point right in the middle, right? Divides all of the cases in half. And so if I come to that judgment, and if there's some way that I can make the mean and the median equal, then why wouldn't I do that? If I think this is a better measure of central tendency, and I can make this equal to this, why wouldn't I do that? And that's the judgment that the researcher has to make. And I think most experienced researchers would come out down on the side of saying, if you believe the median is a better measure of the central point, and if you can transform the data to make the mean equal to the median, then you should do that, because then your data is going to be more reflective of the population that you're speaking to. All right. So there's a whole bunch. There are hundreds easily of transformations that you can do. Your textbook talks about logarithmic transformation, square root transformation, and the inverse transformation. 3 very common transformations. And the strategy that I would employ, and the textbook goes into some details about when to use which of these different transformation techniques. The strategy I would employ is to try all 3 of them. See which of them make your data most normal, and then use that one. Or maybe it will be the case that they all make your data, well, they won't all make your data worse. Maybe it doesn't get much better. Maybe it's still non-normal, right? Which is, in probably more cases than not, ends up being what happens. You try to transform the data, it gets a little bit better, but it's still not good. And then you have to decide, well, is this a battle that I want to fight? Do I want to make the argument that I transform the data to the editor, reviewers? Do I want to make that argument because it raises some concerns with some people for this little bit of gain? And it's a judgment call that you have to make. For me, if it makes it better, clearly better, I would do it every time. If it's only a little bit better, then it becomes a judgment call, depending perhaps on who the audience is. So, but remember that transformations will change the scale that's being used. So if you're using age and you take the square root, do the square root transformation, you're not going to have age anymore. You're going to have square root of age, right? And so it's no longer, it changes the scale, right? And so that is important to keep in mind when you're interpreting the data. And it's also important to keep in mind when you're hoping to, or you're thinking that you're going to combine multiple items into a larger scale, or you want to do some comparison between different scales. And if you take the square root of one of the scales and you don't take the square root for the other scale, you can no longer, you can't compare those, right? If they were both on a 1 to 9 scale to start with, you square root one of them, and you don't square root the other one, don't compare them, right? It'll be garbage. And so you have to just be careful about what you're doing. There would be a number of ways you could fix that. How could you potentially fix that? So you take the square root of one of the scales, and you don't take the square root of another one because it's already normal. How could you potentially fix that so they are on the same metric?
Standardism.
What's that?
Standardism.
Yeah, you can take the z-score. So that, and then just take the z-score of both of them, and then the mean would be 0. Standard deviation will be 1 for both scales. And that does taking the z-score change the shape of the curve? Don't. It just changes the values on the x-axis. The shape stays exactly the same. So far, so good. Questions, concerns? So believe it or not, this is a friendlier version, if I dare use that term, a friendlier version of the table that your textbook has, okay? And so let's take it, we'll talk about positive skewness first, then we'll talk about negative skewness, and then we'll work an example, and hopefully after all of that, you'd be able to do this with your data if you need to do this with your data. So use these 3 columns if your data is positively skewed. So meaning the skewness number is greater than 0, right? And that's what I mean by positively skewed. So let's say it's positively skewed and you're concerned about the skewness, and you want to try to transform the data. And then if the skewness is negative, we use this single column right here. And if it's positively skewed, and all of your values are positive, so let's say we have a scale from 1 to 10, all of our values are going to be positive, we would just use this column right here. And all we would do is compute 3 new variables, one that's the square root, one that's the log, and one that's the inverse of those variables. And then we would assess the normality of these 3 new variables and make a judgment about whether it gets better or gets worse, okay? And so I'll show you how to do the compute statement for this. It's the same, when we calculate the Mahalanobis d-squared probability, it's that same compute box that we'll use to calculate these 3 new variables, and it's pretty straightforward, and we'll go through that, and so you'll see how to do that, okay? So this is if all of yours, you have positive skewness, and remember that this is a simplified chart from the one that's in your textbook, okay? So just keep that in mind that I'm doing everything I can to make this useful. The textbook also goes into when to use these 3, and I say just do all 3 of them, look at all 3 of them and see which one is the most normal, and then use that transformation, okay? So here is, let's say you have 0 in your data, and so the square root of 0 is defined, but the log of 0 is not defined, and the inverse of 0 is not defined either. So we have to add 1 to all of our score, and I just say, okay, also add 1 to this one just to make it consistent. So just take all of your, so if you have 0 to 10, let's say, you're just going to add a 1 to all your scores. So the lowest score will be 1, and the highest score will be 11, right? So everybody just shifts up 1. We have no zeros in the data, because if you try to take the inverse of 0, it's going to, SPSS will say that's not enough. Okay? Make sense? So if you have 0, you have to do this. And so you should be thinking about the data that you're going to be working with and which of these 3 you're going to potentially have to use. You won't have to use, for any one variable, you won't use all 3 of them. You'll just use one of these 4, depending on whether it's positively or negatively skewed, whether you have only positive values, only 0 and other positive values, or if you have negative values. If you have negative values, we add a constant to all of the scores so that the smallest score is 1. So just figure out what that constant needs to be. So let's say our data is minus 10 to plus 10. What constant would we need to add to the data so that the smallest score is 1? Yeah. So we could add 11 to, we could just take each score plus 11, and then take, because we can't take the, well, you can't take the square root, that's not a number, right? The square root of a negative number is not a number. And the log of a negative number is also not defined. But you could take the inverse of a negative number. But just to keep things consistent, we're going to add a constant to all 3 of them, okay? So and the reason we have to do that is because the square root of a negative number isn't defined, and the log of a negative number isn't defined, okay? Make sense? So far, so good?
When we have the 0 value, we don't need to only add the 1. I mean, we can add 1 or 2 or 3 or
Yes.
yeah. But 1 is very easy. You mean, yeah.
If you have a 0, that's all you need to do is add 1 to all the scores, and then you no longer have a 0 in your data, right?
Yeah. I mean, we don't need to add only 1. I mean, we can add 2 or 3 or 4. It doesn't matter. Exactly.
Talk to me more. It does. I'm sort of curious as to why you would want to do that. What do you think in terms of when you would do that? Add something, because here we would add just 1. Here we just add some constant, so the smallest value is 1. What are you thinking about?
Because the value should be more than 0 or something like that.
Yes.
Yeah.
Yes.
I mean, yeah, we don't need to. We use only one when we have zero value. I mean, yeah.
Yeah, if your lowest score is 0,
Yeah.
if the lowest score is 0,
Yeah.
you add 1 to all the scores and everything's greater than 0, right?
Yeah.
If you have negative numbers, then you have to determine what that C needs to be so that all of your scores are greater than 0. I don't think I answered your question.
Okay. Yeah.
Ask me after class
Yeah.
if there's something that I can do to help. I'll be happy
Yeah.
to help. So far, so good. So you just make a judgment about which of these 3 columns you need to. If it's positively skewed, make a judgment about these 3 columns, and then do the transformation. Assess the normality of the transformed variable. Hopefully, it gets better. If it doesn't get better, then you're out of luck. Then you go back to the right. And so, if it's negatively skewed, what we do is we reverse code the data. And if you reverse code a variable, you have to remember that, hey, I've just reverse coded this variable. And when you reverse code a variable, the negative skewness becomes positively skewed, right? And this, taking some constant minus each x, will reverse code the data as long as that k is the right number. So let's say our scores are 1 through 7, and let's say it's negatively skewed. If we make k 8, and we take each score, each score minus k, or take k minus each score, that's going to reverse code the data, right? Because a 1 will become, this will be 8 minus 1 becomes a 7, right? A 7 becomes a 1, right? Because 8 minus, right? So all we're doing is reverse coding the data. Just another way to reverse code data. It works the same way as if you were to do transform, recode. It's the exact same thing. We're reverse coding the data to make it positively skewed, and then we apply the same 3 transformations, okay? Because these transformations in theory only apply to positively skewed data. So we need to, in this case, make our data from negative skew to positive skew, and then do the transformation. Assess the transformed variable to see if it's better. And then if it is better, guess what? You just transform your variable. It's low values are now high, high values are now low, right? And so you can retransform it back. Let's say you decide the inverse works good. You can retransform it back. And the level of skewness will stay exactly the same. It just will switch from positive to negative again. And then you could also, if you want to keep it on some metric that makes sense, you could take a z-score of it as well. So it's a lot of work, but in some cases it's worth doing, particularly if you're really unhappy with the mean as the measure of central tendency. If you really think the median is a better measure. And that's all we're trying to do here, because if we have data and we have a center point in the data, which is the median, right? That, regardless of which of these we do, that person or that thing that's in the center will always be in the very, very center, right? They'll always, no matter what you do in terms of a linear transformation, no matter what you do, that person or thing, whatever your unit of analysis is, will always be in the middle. And all we're trying to do is to move the mean to be more similar to the median or the middle point. And it makes, in my judgment, perfect sense to do it. Perfect sense to do it if you're unhappy with the data. Right? So I'll just show you quickly, or not quickly, however long it takes, how to transform data, and just to make sure that so I say on the next page, or on, I guess it's the next page, next couple pages, that I'm going to work only with one of these three variables, or one of these four variables. I'm just going to start with how the respondent feels towards African Americans and attempt to transform that variable. And if in this case, let's say I wanted to use all four. Let's say these all four were dependent variables or independent variables. Remember, whatever I do to one of these, just keep in mind that it's going to change. If you take the square root, it's going to change the metric, right? If you take the inverse, it's going to change the scale. So you need to keep that in mind. You can't just transform them and then assume that everything is equal after that transformation. You have to do something to ensure that you can still make those comparisons that you want to make with your data. So if we want to try to transform this variable, we can do compute variable, and we get this familiar looking window, right? And you can just call these whatever you want to. And all we have to do is, I think the abbreviation is SQRT. If you didn't know that it's SQRT, you could go here and then scroll down and to the S's and find something that looks like square root. I had it. That looks like square root, and it does tell me that it is square root. So I could also do this, or I could just type in SQRT. And SPSS isn't case sensitive, so I could have done lowercase SQRT or uppercase. And so then I just want to do, is this the one? The first one?
Well, no, that's the second one.
Right? And so then that's going to create a new variable in my data. Okay. Again, the name is, you can call it transformation A. It just doesn't matter what you call it. But square root seems to make sense. And then I'm going to do another compute statement. And this time I'm going to change it from square root to, oh, by the way, was this positively skewed?
You can check.
There it is. So it's negatively skewed. So what we have to do is something, well, we have to do what I actually have in the handout that I just didn't bother looking at as I was doing this. What we need to do is take the large, we need to make it positively skewed. So we're going to just sort of reverse code it, but we're going to do that all at the same time. So
How did you know it was positive? Maybe
I'm looking at, I think I have it on another sheet too, Jackie, but I'm looking at this first column on page 31, and I can see that the skewness for how R feels towards African Americans is negative 0.488. So because it's negatively skewed, that means we need to use that column in the, that means we need to use this column, which says we take k minus x, and I'll tell you what k is here, but k is a score. Usually the greatest value plus 1 will do it. And in our case, the greatest value is 9, not 10. I think I told you 10 a few minutes ago or earlier, but the greatest value is 9, so we're going to just use 10. And it's going to be, I can do this all at one time. Right? So it's 10 minus the person's score. So this is going to be the square, this is going to give me the square root of 10, or k, minus x, if you look back at the previous screen that I had up there. And I'm going to say OK. And I'm going to tell it to replace that value that I erroneously or in error created earlier. And then the next one I want to do is another compute. In this case, I want to do the log. So I'm just going to call this log. And I know that it's just LOG. But if you didn't know that it was just LOG, you could find it over here and move it up there. And it's the same thing. It's K, highest score plus 1, minus each person's score, which will reverse code the data. And we're going to create a new
Isn't it like a LT, not LLT?
oh, it is not that. It's LG10, is that it?
Yeah.
So it's log base 10 of that. Does that look better? So no error means it must have worked. And then the final one is just inverse. And we don't need, all we need to do is to do 1 divided by K minus each person's X score. And so now I have, we go to variable view. I just created these 3 new variables. And so what you have on page 31 is the descriptive statistics that I requested for those 3 variables plus the original variable. So I just did descriptive. I did analyze, descriptive statistics, descriptives, and reset that. And I'm doing African Americans. And then these 3 variables here. And options, I want kurtosis and skewness and standard deviation, and that should be good enough. And here's the output, which it looks close. Maybe I might have, on page 31, it's the same, but it's just in a slightly different format. I think I might have changed the rows and the columns or something so that it fit better on this page. But it's the same information. So what we can do then is look at what I would do is look at our original variable. Our original variable was how R feels towards African Americans, and we see that our skewness there was minus 0.488, right? And we can look at the square root, and it's 0.025. A lot better, right? Divide it by its standard error, and it's less than 1, right? So that tells us that it's probably not significantly skewed. And just to continue, if we look at the log, it got better, but it's greater than, if we take the ratio of minus 3.2 divided by 0.095, that is greater than 1. And then if we look at the inverse, that one got quite a bit worse, right? That one actually got worse than our original skewness was minus 0.488. In absolute terms, this one's worse because it's 0.717, right? So the only one that would make some sense to at least look at more carefully would be the square root transformation, right? Because the skewness is better. But what else would you look at? Yeah, and how did it do?
Got worse.
It got way worse, right? So no free lunch for us. I would not use it. I mean, because you're fixing one problem at the expense of causing another problem, and it just isn't. If this was sort of the end of this is all I can do in terms of transformation, I think probably what you do is you end up using your original variable as opposed to the transform variable, because the transform variable is not in total any better than actually the kurtosis got a lot worse, didn't it? And so and that's the life of a data analyst. That's the way things work sometimes. And so it'd be your call, but my judgment in this case would be, boy, it's going to get a little bit better, or it's going to get a lot better in terms of its skewness, but it's going to get worse in terms of the kurtosis. It's not worth. There's no gain in terms of analyses. Make sense? Questions?
And the first step was checking to see if our skewness and kurtosis if it's significantly skewed or.
Yeah, and so you'll either look at the histogram, or you'll look at the ratio of skewness to the standard error of skewness and kurtosis to the standard error, and then make some overall judgment about the normality of your data. And then if you deem that it's not normal, in other words, you say that the median is probably a better central place or central point than the mean. And if you make that judgment, then doing transformations would be the next step. Go ahead. Good.
So if we decided if the kurtosis looked better on this, and yes, the square root transformation works, what do you mean? Because you said go back and do it for all scales, or?
Well, we'd have to do something because now we have the square root of how they
But
feel.
Everything we have.
Well, whatever let's say we're just doing t-tests, for example, and our t-tests are going to be paired sample t-tests between people's feelings towards these different groups. Well, we wouldn't want to compare the square root of a 1 through 9 scale with something that's not the square root of a 1 through 9 scale. So we'd have to put those scales on the same metric, right? Because if we take the square root of everything, now the lowest value is going to be the square of 9, right? The square root of 9.
But what if it makes this kurtosis and skewness amazing?
Yep,
So
that's
then we
good.
do the
It's all
square
good.
root on others, and it makes them awful.
But we don't have to do it on others. We just have to make sure that we do something to make them. So we could just convert them all to z's. So let's say we try it with the other 4 or the other 3 Asian in this data, Asian Americans, Hispanics, and Caucasian. And this is the only one that. Let's say this one works. Let's say this is the only one that works. The other 3 don't work. We want to transform this one because we really think it's a better thing to do. Then what I would do is make z-scores for all 4 of them. Then they're all going to be on the same metric. Mean equals 0, standard deviation equals 1.
But don't we run tests using different scales without making them the same?
And if you're comparing means on those scales, then I don't think I do. Can you give me again?
If one, was on a scale of 1 to 7,
Yeah,
and then you asked him on from 0 to 20.
yeah.
Or it was, on a scale of 1 to 7, and then this other one was a semantic differential
Yep.
scale with 10 points. Like, we compare those.
You better not be. You can do a correlation between the two because a correlation will put it on a.
Oh, no, yeah, we wouldn't do a t-test.
Oh, right, and that's what I'm thinking.
Yeah.
Right, I'm thinking some kind ANOVA or some kind of mean comparison where we're calculating a mean based on these. But
Correlation? Okay.
and
Good.
regression would probably I think regression you probably would want to put them all on the same metric as well. With regression, you do have standardized coefficients, sort of like a correlation coefficient from -1 to +1. So you would have that you could look at. But to make it simple, I would transform them. Make sure they're all on the same metric. You may not transform them all. We're only going to do the one, but we have to make sure that the other 3 that they're comparable. And the only way we can make that comparable, well, there'd be probably a number of ways we can make it comparable, but the way that I would fix it would be to take the z-score for all of them. And the z-score is not going to, The one that we fixed is going to stay fixed, right? We just take the z of that, and it stays exactly the same shape. We fixed it, and then we just put the other three on the same metric. So they're on a, mean equals 0, standard deviation equals 1.
It's still confusing back to
Let's talk about it. What else?
Because if we're using age as one of our variables, I've never changed age into anything. And that's, 0 onto the highest.
But are you doing a t-test where you're comparing the square root of age, which is what we're doing. This is, right, you wouldn't compare the square root of age with age, right?
No.
That'd be, right. And that's what I'm saying we need to avoid. And so if we take the square root of this variable, and we try to do a paired sample t-test between this one and this one, it's going to be garbage in, garbage out, right? And so we have to put them on the same. And so all I'm saying is take the z-score of both of those, and you'd be good to go.
Okay.
You fixed the problem with non-normality, and you've also avoided embarrassing yourself by doing a t-test with two variables that are measured on two different scales.
Yeah.
And I know you haven't done that.
That I get.
Right.
Okay. Because I'm just thinking, no, I'll, run an ANOVA, one independent variable. I have multiple dependent variables. Those dependent variables are different scales.
Of course. Of
Okay.
course. And that,
That's
right.
what I thought you were
right.
saying was they had to be the same. Like, wait, we don't do that. Okay.
Right,
I'm good.
right,
Okay.
yeah. And that is not so subtle of a difference, but it is a difference for sure. And you just have to think carefully about what it is that you're gonna. If you're just gonna do correlations, it doesn't matter. You can correlate the square root of something with something. So we could do a correlation between this and this without taking the z-score both, and it's going to be exactly the same as if we were to take the square root of, or turn them both into z-scores. Other questions? Everybody good? On a scale of 0 meaning despair, 10 meaning can't wait to get home and get this done, where are you?
I can't wait to get this done.
But you may not. You may watch football tonight instead of doing your homework. Elena, you look like you're going to say something. That's why I called your name.
Yeah. What if we don't have outliers?
Then you're all good. Just show me that you don't have outliers. Yeah,
Okay.
yeah. Just show me. However you made that judgment, show me that you didn't have.
And if
You don't
we
have to.
Normality and no issues. We just say
You're good.
We're good.
But show me the data, right? And
And it's only with the variables that we already previously discussed.
yes. So you don't have to add in a whole bunch of new variables. Don't add in a whole bunch of new variables. Just the same variables that you've been using all along. If you have nominal variables, don't be taking the square. Don't try to transform those don't be assessing the normality of a nominal variable, because I will take points off because you shouldn't be doing it. Right. Okay. So, other good questions?
So when we're showing you the SPSS output and the syntax and everything, and we're talking about the outliers, since what you get is that table that means nothing, what should we show you?
What table means nothing?
When we do the linear regression for the
Yeah. So you could just show me the syntax for the. Good question. Show me the syntax for the Mahalanobis.
that we did the test.
Yeah, and so it could be both the regression syntax, and then when you do the compute statement, there will be another little snippet of
Right.
syntax. Show me that, and then you can. There'd be a number of other ways that you could do a screenshot of the lowest scores, or you could do a frequency table
Okay.
of those scores to show me the lowest scores. And if you didn't have any problem, you could say, hey, my lowest p-value was 0.01, and I don't have any issues with multivariate outliers.
Okay.
Good. Other questions?
What if all of our variables have outliers? You have to transform all of them?
So that's like 4 or 5 variables, right? Yes. So yeah. So to answer your question, yes. If they all have outliers, you would just do that for. But when you do one, to do 4 or 5 is not 4 or 5 times more work. It's maybe 10% more work. You tell me when you're done, okay? But I think it's not 4 or 5 times more work. And if you really think they're all, well, how many variables are you working with?
I use 4.
Yeah, so you'll be good. All right. Anything else? So in this case, just to sort of put a period on this long-winded conversation, I don't think I would want to pay the price to use this variable to replace this variable because it gets better in one case, it gets better in terms of skewness, worse in terms of cortosis. I would stick with the original variable and just report that it was non-normal in a sentence in my write-up. Okay, and then is that the last slide? Is that the last? Goodness. So in conclusion, you have to use your judgment about when to do this. There's no black and white. P-value is less than something, then absolutely do it. It's a judgment call. There's a lot of gray area. You'll need to make the call yourself. I would say if significant improvement can be made without compromising the interpretation of the data, which let's say we're working with SAT scores or ACT scores or IQ scores or something, if you square root them or inverse them or take the log of them, it's going to compromise the interpretation of that data. And if that is a problem, which it might be in some situations, then you might think twice about doing this, especially if the improvement is only marginal. And you'd also want to think about who your audience is. So in my dissertation, I wanted to transform a bunch of variables in my data that I worked with. And one of the people on my committee just thought that was cooking the books. And so I was not allowed to cook the books, even though I knew that it wasn't cooking the books. It was just, but that's the way some people process it. And so keep that in mind. And so as your I think most people though would come down on the side that if it doesn't hurt interpretation and it makes the data more normal, it makes perfect sense to do that. And the people who say no, that's cooking the books, may just not have had this class, right? Or may just not have had a good stats class to help them understand that it's not that, it's actually making the books better. We're trying to, again, make that mean value that we don't think is a very good measure of central tendency. We're trying to make that equal to or closer to the median value. And so there's just a quick blurb in terms of how you might report transformation. Okay? Questions? Zero? None? All right, so I could tear into correlation and or just bivariate simple regression, and we can talk about that for 15 minutes. But I'm not gonna. So we're gonna be exactly 1 week behind, but we'll easily catch up if you look at the schedule. Have faith. We have one class period that is catch up, and we won't get more than one class period behind. So we're going to stop here tonight, and we'll start next week, and we'll cover all of next week's material next week for sure, and probably start some on the multiple regression material that you need to read, and then you're going to get another homework assignment next week that probably won't be due the week after.